Today we're going to look at generating our first two exponent laws, okay? And this is going to show you where it comes from. Now you won't need to do this every time. Once you've got that law down, you can just continue to use it to make your life simpler, okay? So what we're going to do is we're going to expand this expression and then write it as a single power afterwards. Okay, so if I was to look at this 5 exponent 3, that means the 5 is repeating itself 3 times, so it's 5 times 5 times 5. In between my two powers, I had another multiplication sign, so I'm still multiplying. And my second power was 5 exponent 4, so that's 5 times 5 times 5 times 5. And when I write this out, all I'm doing between all of these 5s is still just multiplying, right? Even this operation in between the two powers was multiplying. So it's really like I'm multiplying now when I count them. 1, 2, 3, 4, 5, 6, 7 5s are all now multiplying together. So another way I could write that as a single power is 5 with an exponent of 7. Okay, and if you were to multiply all those things together, it's 78,125, and that's the same thing if I had done each of these separately. If I had gone 5 exponent 3, it's 125, and 5 exponent 4 is 625, and when I multiply those two guys together, I get 78,125. Okay, so when I write it as a single power, I had 5 with an exponent of 7. So let's do another one just to see. Maybe you're noticing some kind of pattern you think might be happening here. So let's try another one. Let's go, we'll say 2 exponent 2 times 2 exponent 7. Okay, so if I was to write those guys out, I'll do the same thing as I did before. So 2 with an exponent of 2, that's the same thing as 2 times 2. And then I am multiplying in between those two powers. And my second power, 2 exponent 7, 2 times 2 times 2 times 2. I should have chosen one with less 2's. Alright, so there's 7 orange 2's. And again, all I'm doing is multiplying in between all of these 2's. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 of those 2's. And that gives me 2 exponent 9. And 2 exponent 9, if I was to multiply all those 2's together, is 512. And that's the same thing if I went 2 squared and I got 4, and then 2 with an exponent of 7, which would have given me 128. And if I go 4 times 128, I still get 512. So these things are equal to one another, right? So I had 5 exponent 3 times 5 exponent 4 gave me 5 exponent 7, and I had 2 exponent 2 times 2 with an exponent of 7, and that gave me 2 with an exponent of 9. And hopefully you can see the pattern here that really all I'm doing is I'm taking those two exponents and adding them together to get that second exponent. Okay, and that's really our first exponent law. Okay, so the first exponent law is called the product of powers. So this is our first one. It says if we are multiplying powers of the same base, okay, we're going to keep the base the same and add the exponents. So there's some keywords here. If multiplying powers that have the same base. Okay, so this only works in that instance. When we're multiplying and the powers have to be the exact same base, then we're going to keep the base the same and add the exponents. Okay, so another example of that, and I won't figure out what this one equals, but I could make this really difficult. I could go something like 7 exponent 12 times 7 with an exponent of, we'll say 15. That would be the same thing as 7 with an exponent of 12 plus 15, because both bases are the same. Both bases are 7. We are multiplying those two powers, and so I'm going to add them together, and I get 7 with an exponent of 27. Okay? Now it works even if I have 3 things. Okay, so if I was to add another power of 7 multiplying or a fourth power of 7 multiplying, I can still add all the exponents so long as they are all the same base. Okay, so that's with it in numbers, but I'm going to give you in algebraic terms. So this is what we look at. So if we've got a with an exponent of m times a with an exponent of n, that's going to equal a with an exponent of m times n. And we say that a, m, and n are part of the real numbers. Okay? Okay, so it works for any numbers that we can put in. Now we're only going to focus on this year exponents that are whole numbers, so we're not going to worry about anything negative. We will talk about zeros, but we're not going to worry about anything negative. We're not going to worry about any fractions or decimals. We'll save that for grade 10. Okay, so that's our product of powers. If we multiply two things with the same base, then we add the exponents together. And I guess I should write add instead of multiply. My goodness, Mr. T, what in the world are you doing? Okay, so we're going to add the two exponents together. Okay, all right, so that's our product of powers rule. Now, let's look at the next one. So this one, I'm going to expand and again write as a single power. So let's look at the numerator of this division. Okay, so this one, 5 exponent 6, that would be like 5 times 5 times 5 times 5 times 5 times 5. Okay, and then I still have that line in my fraction to keep my numerator and denominator separate. And then in the denominator, I've got 5 times 5 times 5 times 5, and that's my 5 with an exponent of 4. Okay. Now what I'm going to do with this fraction, we like to put fractions in lowest terms. And when I want to put something into lowest terms, I look for a common factor between the numerator and the denominator. And it just so happens that between the numerator and denominator, I know I have a common factor of 5, right? I have this 5 right here and this 5 right here. So if I was to divide top and bottom by 5, right, those guys would cancel and they would turn into 1s. But then I still have another common factor of 5, don't I? I got this one and this one. That's a common factor of 5. So we'll cancel those guys out and they become 1s. But I still have another common factor of 5, right? This one and this one. And I got one more common factor of 5, this one and this one. And so what I've changed my multiplication into is now 5 times 5 times 1 times 1 times 1 times 1 over 1 times 1 times 1 times 1. Well, multiplying by 1 doesn't do anything, right? Anything multiplied by 1 is still the same thing. So up top, it's 5 times 5, and that's it. In the denominator, 1 times 1 times 1 times 1 is just 1, so I have a whole number. So I'm going to get rid of those 1s. And now I have no need for this line. And I have 5 times 5. And 5 times 5 is the same thing as 5 squared. Okay, so that gives me 25. Okay, so 5 to an exponent of 6, if I was to do that one separately. Okay, so 5 with an exponent of 6 was 15,625, and 5 with an exponent of 4 is 625. And if I was to take 15,625 and I divide by 625, I get 25. Okay, so I get the same thing. Let's do it with another set of numbers. Let's try another one. Let's do 3 this time. Okay, here we go. Let's go 3 to an exponent of, let's say 5, divided by 3 with an exponent of 2. Let's see what it looks like. So if I was to expand, that's 3 times 3 times 3 times 3 times 3 for my numerator, and then 3 times 3 in the denominator. And as I look to find common factors to put into lowest terms, common factor of 3, and another common factor of 3. Those guys turn into 1s. So what am I left with? I'm left with 3 times 3 times 3, and that's the same thing as 3 with an exponent of 3, and that is 27. Well, if I'd done 3 exponent 5, that's 243. If I do 3 squared, that's 9. 243 divided by 9 is still 27. Okay, so let's look at what we had. I'll write it out again for you. So the first one we had 5 exponent 6 over 5 exponent 4. Now that is the same thing. I didn't write it like that, but it is the same thing as dividing, right? I just had it written as a fraction. And that gave us 5 exponent 2. The next one we had 3 exponent 5 over 3 exponent 2, which would be the same thing again, 3 exponent 5 divided by 3 exponent 2, and that gives 3 with an exponent of 3. So hopefully you can see, hopefully you notice this pattern. Since I was dividing, the exponents ended up subtracting to give me that 2, right? Since I was dividing, these exponents ended up subtracting. 5 minus 2 gave me that exponent of 3. And that is our second of the exponent laws. So it's called quotient of powers. When dividing powers with the same base, we're going to keep the base the same and subtract the exponents. So again, I'll give you some difficult numbers that you wouldn't actually want to end up typing into your calculator. So let's say I had 3 to an exponent of 27 divided by 3 with an exponent of 20, we'll say 23. Well, since they're dividing, I'm going to write that as 3 with an exponent of 27 minus 23, and that gives me 3 with an exponent of 4, and that would be the same thing as 81. So I now took what would be really difficult to type into your calculator. I don't even think you probably have enough digits for it to show you, and I can figure out the answer very simply. Okay, so here's how it would look in algebraic terms. So it's a with an exponent of m over a with an exponent of n, and that could also be written instead of as a fraction. You might see it as a division statement. Okay, either way the base is still the same and we are dividing. We're going to write that as a with an exponent of m minus n. Now with this one we do have a small caveat that we need to add in. I need to say that the base cannot be 0, because if I have 0 as a base and I put that into the denominator, I'm now going to end up trying to divide by 0, and as we've seen in the past, if we try to divide by 0, your calculator may and or may not spontaneously combust, and you definitely don't want to start calculator fires within your home. So don't try to be dividing by 0, make sure your base is not 0. Okay, so again, key words from this one. So when dividing powers and it's with the same base, so we have to make sure that the base is the same, we get to keep the base as it is and subtract the exponents. All right, there's your first 2 exponent laws. Next couple of videos, I'll give you the other 4.